Okay, hello everyone. In this tutorial I will show you the mesh-to-mesh approach, which belongs to the moving mesh family and allows for doing those cases when large deformations are considered, and the more traditional approaches for dynamic meshing are not usable because the quality of the mesh usually degrades when the displacement is considered, and sometimes it reaches a point when the simulation might blow up or simply give not reliable results. With this approach, the meshes of the different time steps are provided beforehand, and the solver takes care of the interpolation. So the case that I will run today, it's quite simple. It's the one that you can see here on the left side of my screen. Is this cylinder with a piston and a valve. In my simulation, the piston moves toward the positive z direction, while the valve moves toward the negative z direction. In this case, the two movements are a linear acceleration for both these components with different values. Okay, so I prepared two cases. One without the mesh-to-mesh approach and one with the mesh-to-mesh approach. Okay, we can start with the case without. So in this case, the setup is quite simple. We do have the usual zero folder in which we have, in this case we have pressure, velocity, and point motion, UZ. Why did I set UZ? Because I only want the Z direction to be displayed. All the other directions are not displayed. It doesn't change a lot. Apart that, in this case, we do have only one component instead of three components. So the setup, it's simple. As I said, it's a linear acceleration. I have two different laws, one for the piston, one for the valve. So for the piston, I have that this is the law of acceleration, and for the valve, I have this other law of acceleration, but we won't reach this value. Never mind. So this is the setup for the boundary conditions. Then in the constant, I have the dynamic mesh dict, which is important in this case, and it's quite easy. As I said, the displacement should be provided in the form of the velocity, the motion of the points. So the mover is the velocity component Laplacian instead of the simple component Laplacian, and this is mandatory for based on my experience, is mandatory for the mesh-to-mesh approach. So we provide this, and since I'm applying the displacement only in a direction, you should provide that direction, and then you choose the way to diffuse your points. In this case, I choose the inverse distance, applied both for the piston and the valve. Then the other setup is pretty standard, and also in system there's not a lot to see apart that in contradict you choose the moving mesh for the solver. Okay, maybe in this case you might see version 10, but actually I'm running with the latest version, the 13. So what happens when we run? Okay, this is pretty straightforward. So we source our environment and then we run. Sorry, not this one. We have the script to run. So all run parallel. Okay, we wait for a few seconds for this to finish running, or maybe a few minutes. No, okay, it's a matter of seconds. Okay. Okay, so what are we going to do next? Well, let's start by looking at the quality. So let's run our check mesh and save it in a log file. This should take a few seconds too, not too much. Okay, now if we look for the mesh should be mesh non-ortho something. Okay, if we look for this keyword, we save this quantity for each time step, which is each 10th of second. And as you can see, the max orthogonality goes from 56, which is a very good value. It starts raising, and then it ends up with the max orthogonality of 82. And in this case, I just run for 1.5 seconds, more or less. But for longer time step, for sure, as you can see the trend, it keeps rising. But already here, when you have a large non-orthogonality as 82, you might work with your numerics to have results, not to make it blow, and to have some results. But as you probably know, this is a pretty high value of non-orthogonality, so it's better to use a different mesh. But in this case, it's not possible. So if we go and look at the case file, you will see that the mesh will start showing some bad faces, bad quality cells. Okay, by the way, these meshes are not done with SnappyX mesh, but with Salome. And the reason behind that is that unstructured mesh handle much better the deformations. So I choose to use this tool instead of SnappyX mesh. But yeah, this is not the important part. But as you can see, the cells are stretching a lot here, and they're compressing a lot on this side. But this is the movement that I want to apply. So this is the first approach, the traditional one, okay? Okay, now we can move to the case with mesh-to-mesh, okay? In this case, the zero folder is pretty much the same, okay? This is not important. You see, this is the same. And there is only a difference. The only difference is that in the dynamic mesh, you see this folder, this snippet. In the snippet, you see that I'm calling the mesh-to-mesh. And in the mesh-to-mesh, I'm providing two time steps. These two time steps are time steps that I previously choose as a time step when the quality was degrading too much and I didn't want to run anymore with that mesh. But I wanted to do another mesh, a new mesh, and I wanted the solver to restart from that point. Okay, so 65 and 96. Then the time delta t is something related to the time marching, but if you keep this one order of magnitude lower than this, and usually the same value as the time, the delta t in the contradict, it's fine. If it raises the error, you can just try to make it lower, but it should work with this rule of the thumb. Okay, so this is the modification in the dynamic mesh dict, and then as you can see in the constant there is a new folder which is meshes, which was not there in the previous case. Instead of meshes, you hold the meshes of the time step when you want the solver to interpolate from one mesh to the new one. Okay, these meshes should be provided beforehand by the user, and you can simply run your simulation, see when the quality of the mesh is no longer good enough according to your standard, and from that point you simply evaluate which is the position that your component have, and do a new mesh and place it inside the meshes folder in a folder with the time when you wanted the remeshing to take place. Okay, so if we now move inside of this, okay, and we look the case. Okay, we should okay, no, sorry, it's probably not here. Wait, let me try something. No, okay, never mind. This is not useful, but okay. So this script is a little bit different with respect to the previous one. In the previous one, we only had the compose part and the run parallel foam run and the reconstruct part. In this case, we have a few more steps, which involve the decomposition. As I said, the first one is the decomposition of polymesh into the various processors. Then what are we going to do is for each time inside of this list, we run the decompose part and we save the log inside the file with the current map time so that it's easier to see. And then we had this mesh map time. So this reads the meshes inside this file and decompose. So in the different processor, you will find a folder with this mesh. Okay, so you will find something like this. And the map time is 065, 096. So in this case, I only have two meshes, two map time and two meshes. But if you add more, you will find a lot of this. So we can try to run only this. So, okay, let's do this. So, okay, so now we have all the processor, and inside the folder constant, inside the processor constant, you find the folder with the mesh. And then if we run this, you see that inside constant, I mean, in any of this, you have meshes, and inside of the meshes folder, you have the new decomposed part of the mesh at that time step, so 065 and 096. Okay, let's see if it's possible to see this. Oh no, okay, it's not possible to see this, but never mind, you will see that after running. Okay, so we do have the processor, and now if we run the solver, okay, we just give it a few seconds. You can follow the solution. It takes, it doesn't take a lot of time, but it's interesting to see what happens when we reach the 0.65 time step, 0.65 seconds. Okay, so as you can see here, it's mapping mesh to the new time step. So it recognizes that we want the solver to stop using that mesh, the initial one, and start using the new mesh. And then in that moment, it will create an interpolation from the initial mesh to the new mesh. Okay. This number should be very close to 1. Okay, if it's far from 1, it means that the most probably the patches, the boundaries, do not match perfectly, so they are too far from each other, and in that case, it can blow up. I mean, it tries to interpolate nevertheless, but if they're too far from each other, it will probably blow up. Okay, So let's see if it's still running. Okay, now it finished. Okay, so now we do have inside of processor all the time step. We can reconstruct them. Okay, now we can run again the MPI run check mesh in parallel. I mean, also in serial. Okay, let's run in parallel, which takes a shorter time. Okay. And now let's do the same that we did previously. Sorry. Okay, so if you remember what we found previously, I don't know if I still have it open here. No, okay, I don't. But if you remember, the mesh quality started at the same level, more or less. I mean, not exactly the same level because the mesh is the same. So in the previous case, I just let the initial mesh run till the end. In this case, I use the remeshing. So we start at the same level of non-orthogonality. Then the quality grow up to 61. And then what happens? Here, the remeshing occurs. So probably if we look for this line inside of it, so let's see. Okay, yeah, 65, as you can see, it's the last time step of the initial mesh. Then the remeshing take place. And after that, the quality is lower. The quality is higher. I mean, the orthogonality is lower. And this occurs again. So it, okay, we are here. We start going up to 62. And then go down again. So probably this should be the moment. Okay, 96. Yeah, exactly. The latest time step of that mesh. And then the remeshing takes place again. And then it goes till the end with the final quality of 56. Okay, so in this case, the quality was not too bad when I did remeshing, but usually you wait till the end of the, I mean, till you think that the quality is getting too bad. Do not wait the latest moment available. So play a little bit in advance so that the quality keeps high. I mean, it's always high, but in this case I wanted to do it the remeshing not too in a short time because of I didn't want you to wait I don't know, half an hour for the mesh to become too bad. But as you can see, this is what happens when you do mesh to mesh. Okay, so now if we look at the mesh, you will see that at those time steps, the mesh, it's interpolated from one case, from one mesh to the newer one. So just, okay. So if we start running, you see it's similar to what we had previously. Okay. So let's try to, oops, sorry. 06. Okay. This is the latest time step. And then what happens? As you can see, if I go one time step ahead, before, this is one mesh, and then the following time step, it's a new mesh. Okay. What happens with the various fields is that they are interpolated, and you can barely notice the interpolation in the measured quantity. For example, if you do put some probes or things like that, there is a very small oscillation, but it's just one time step, and then it's smoothed out. So if you, look at the average value, it's almost not visible. Then something similar happens at 96. So this is 95, 96, and then it remeshed. Okay. And then it keeps moving till the end. Okay, probably now, the quality is still high, but if you keep doing that, you should probably remesh a few more times to reach the maximum extension of the valve. Then it should go back ideally, and the piston keep moving toward the top. Okay, I think that this is all. So the key differences are in this script, in which you should only be aware that you should decompose the meshes contained inside of meshes, inside of each processor, if you want to run it in parallel. Otherwise, if you run serially, you don't need this, but I mean, why not? And yeah, in the dynamic mesh, remember to put this snippet, the topo changer, with this keyword and the times when you want to remesh. Okay, that's all. Bye bye.